Let's work the following problems in this table. We're going to look at some fixed decimal notation and some scientific notation in terms of the number of significant figures and the uncertainty. Convert back and forth between the two. We're going to apply the significant figure rules that we learned from the video. First number, 123. We start counting from left to right with the first non-zero digit, which is 1. We count to the last significant digit, which is 3. So there are 3 significant figures. The uncertainty is with the last significant digit, which is a 3, which means our uncertainty is in the ones place. So I'm going to record that as plus or minus 1. We write the number in scientific notation. We write it as a number between 1 and 9. So 1.23 times 10 to how many decimal places we moved, which is 2. And since we start out with a number greater than 1, our exponent is positive. The next example is number 20, and I want to compare it with the following number example, which is 20 with a decimal. They're different in terms of the number of significant figures that they have and what they're trying to imply. 20 without a decimal tells us that our uncertainty is really plus or minus 10, that our last significant digit is the 2. And so there's only one significant figure. It's all because there's not a decimal point that we can actually see. When we write this number in scientific notation, it'll be 2 times 10 to the first. We start out with one significant figure, we'll wind up with only one significant figure. Whereas number 20 with a decimal, the decimal implies our uncertainty is with a 0, which means our number is plus or minus 1. So the number of significant figures we have is 2. So when we write the number in scientific notation, we also have to have 2 significant figures. So the answer is going to be 2.0 times 10 to the first. This can be confusing, so make sure that you understand what we're doing in terms of identifying the uncertainty when there are numbers at the end of a 0 with or without a decimal. The next 3 examples will further use this concept. We have 800, 800 with a decimal, and 800.0. In the first one, there's no decimal, so the last non-zero digit, looking from left to right, which is 8, is where our uncertainty lies. We've only got the one significant figure, and it's in the hundreds place, so our uncertainty is plus or minus 100. We write the number in scientific notation, number 1 to 9, so it's going to be 8 times 10. We move the decimal point 2 places. So we start out with one significant figure, we wind up with one significant figure. It's going to be 8 times 10 to the second. With the number 800 with a decimal, now all 3 digits are significant, all because we actually see a decimal. Because now the uncertainty lies with the second 0, which is in the ones place. So our uncertainty of the overall number is plus or minus 1. When we write it in scientific notation, we start out with 3 sig figs, we have to wind up with 3 sig figs. So the answer is going to be 8.00 times 10 to the second. The next one is still the number 800, but that's 800.0. Because of the decimal, all those trailing zeros become significant. So there are now 4 significant figures in the number. Where the uncertainty lies is in that last 0, which is in the tenths place. So we're trying to show that the uncertainty of this number is plus or minus 0.1. So when we write the number in scientific notation, if we start out with 4 sig figs, we have to wind up with 4 significant figures. And since we moved the decimal 2 places, we start out with a number greater than 1. Once again, it's 8.000 times 10 to the second. Make sure that you understand the difference between the answers that we've written for these last 3 problems. 0.023. The 3 is where the uncertainty lies. The preceding zeros are not significant. They're never significant. So we have 2 significant figures. Where the uncertainty lies is with the 3. So it's plus or minus 0.001. The 3 is in the thousandths place. So our answer in scientific notation will be 2.3 times 10 to the negative 2. We move the decimal point 2 places, and it's a fractional number, so that means our exponent is going to be negative. Whereas the number 0.0230, zeros at the end of a number are significant if you see a decimal, and we see a decimal. So now that trailing 0 becomes significant. We now have 3 significant figures. So if we write this in scientific notation, we'll have to have 2.30 times 10 to the minus 2. Minus 2 because we moved the decimal 2 places, and it's negative because the number is less than 1. And so what we're trying to convey in this number is that the uncertainty is plus or minus 0.0001, because that is where the uncertainty lies. So in the 10,000th place. Last 2 examples are going to be a reverse process. We want to write 6.7 times 10 to the positive 2 in fixed decimal notation. So 7.7. We need to add a 0 because of the exponent 10 to the second. There's no decimal point that we write because we can only have 2 sig figs. We started out with 2 sig figs in the significand of 6.7 times 10 to the 2. So we can only have 2 sig figs, 2 significant digits in our fixed decimal notation. So our uncertainty winds up being in the tens place, as the 7 is the last significant digit. The last number, 8.30 times 10 to the minus 3. We've got 3 significant figures. The 0 in this problem is significant because it's found at the end of a number that has a decimal point. This is going to be a number that's less than 1 since we have a negative exponent. So 0.00830 will be the correct answer in terms of writing this number in fixed decimal notation. So now the uncertainty is in that last 0. So our answer is going to be 1, 2, 3, 4, plus or minus 4 zeros, 1. If you don't understand the concepts, please go back and look at the book, the notes you've taken from the book, look back at the introductory video, and you're always welcome to chat with me either in person or electronically, or to send me an email. Thanks.